In Faraday's time, it was known that electric current creates a magnetic field, but it remained a question whether the reverse is possible, if a magnetic field could generate electric current. Faraday answered this question with his most famous apparatus, Faraday's electromagnetic induction ring. So the current induced in the coil only when the magnetic field through it was changing. So this lab will demonstrate Faraday's law of electromagnetic induction.
First, we will talk about magnetic flux. So phi equals BA. Phi is the magnetic flux, B is the magnetic field strength, and A is the area of a B enclosed by the loop. So if we take the derivative of d phi with respect to dt, which is equal to dBA dt. So for the dBA, is B changing or is A changing? Or maybe both? Actually, we're going to keep the B constant and move the loop through the field. So does the area of the loop actually change? No. So what changes is the amount of a magnetic field enclosed inside. So this shaded area is A. Does this area change as the loop moves forward with a speed v? Yes. So as the loop moves forward, more of B is enclosed. And if v is constant, the rate at which the field is enclosed is also constant. So the dA equals dx times h. The rectangle is equal to base times height. So delta x, so this is the change because it's going to increase as the loop moves to the right. And h is not changing because it remains constant. So we got dA dt is equal to dx h over dt, and that is equal to dx over dt times h. So dx dt is basically velocity times h. So we got dA dt equals v times h. So finally, we've reached the conclusion that d phi dt for a single loop is equal to d phi dt is equal to b times vh. So you can think about using this loop of a wire to trap magnetic field lines. So the greater the area enclosed by the loop, the more field lines you can enclose. So the stronger the magnetic field, the more field lines there are, and so there are more field lines can be enclosed. So now we're going to talk about Faraday's law. So epsilon equals n times d phi dt. So according to Faraday's law, changing magnetic flux induces a voltage across a wire loop. So if you make a coil having n loops, the voltage increases by a factor of n. So epsilon is equal to n times d phi dt. So in this equation, epsilon is the induced voltage, phi n is the number of loops, d phi is the change in magnetic flux, and dt is the change in time. Since we have figured out the flux change for one single loop, so we can put the pieces together. So we can substitute for the change in flux, which is to figure it out. So we got epsilon is equal to nbvh. So the loop entering and exiting the magnetic field gap is as follows. First, the magnetic field B is constant, and the loop is moving with constant speed v. So none of the field is enclosed, so epsilon is equal to 0. Next, once the loop enters the field, the rate at which the area enclosed increases. So the rate at which the area enclosed increases is constant. So as long as the area enclosed keeps increasing, the voltage will remain constant. So epsilon is equal to NBHV. Next, when the loop is completely within the B field, the area enclosed no longer increases. So the enclosed area remains constant and equal to the area of the loop itself. So dA is equal to 0 and epsilon is equal to 0. Finally, as the loop emerges from the field, the rate at which the area enclosed decreases is constant, the same as the rate of increase. As long as the area enclosed keeps decreasing, the voltage will remain constant. Epsilon here is equal to NBHV.
Hello, so this is a lab for electromagnetic induction. And first I will give you a very brief overview of the lab. You will explore Faraday's law, the relationship between the rate of change of magnetic flux and the electromotive force, EMF. And you will apply Faraday's law to a coil moving in a magnetic gap and use the measurements to determine the value of a B field in a gap. And then you will analyze a second scenario where you will use a Lorentz force to determine the B field in the gap. And finally, you're going to compare the values for the B field using these two methods. So in the first section, the electromagnetic induction demonstrator, you're going to demonstrate the connection between electricity and the magnetism. And you're going to define the magnetic flux and develop a method to measure it. In the second section, you're going to apply Faraday's law to a square coil of a wire moving through a magnetic field and calculate the unknown B field. You're going to plot EMF versus velocity, and the equation for the line is epsilon equals NBHV, where N is the number of coils, B is the flux density, and H is the height of the coil, and V is the velocity of the glider, and the slope is NBH. So if you know the N, you know the H, you can find out the B field. And finally, you are going to observe the force on a current carrying wire and use it to predict the strength of an unknown magnetic field. And you will plot a force versus current, F versus I. So the magnitude of the Lorentz force, F, is equal to ILB, and the slope of the line is LB. So you're going to measure the length of the conductor and then figure out the B. So as you know, Faraday's law is the key to Maxwell's equations, and you cannot separate the electric from the magnetic. So according to Faraday's law, a changing magnetic flux will create a voltage across a loop of a wire. So this is the foundation to the alternating current, motors, and generators. So the first video here shows an apparatus to demonstrate the electromagnetic induction, and you can watch without making any measurements, just paying attention to what happens when it happens and what changes. In the second section, you're going to measure the induced voltage, the EMF, and measuring it is a little more subtle than it seems. So you're going to watch the video and notice that the voltmeter reading is not constant during the entire trip through the magnetic field. So you need to watch the voltage and catch the voltage at either end, but not in the middle. Also, when you record voltage values, don't include the sign. Use the absolute values. So you need a number of measurements to get a reliable average of the voltages at either end of the gap. Notice that you're going to take data as the loop enters, and again as it leaves the magnetic field. So you are going to record 4 EMF values as the loop enters the magnetic gap, and another 4 EMF values as it leaves the magnetic gap. Make sure you are recording the voltages in absolute values, and then you are going to take the average of the 8 values and use that voltage value as the EMF for each video trial. And we have 5 video trials. Each video trial has a different glider speed. So for the 4 data points as the loop enters and another 4 data points as it leaves the magnetic field, I'm suggesting these 8 positions. So when you are aligning the positions, basically you're going to notice that there's a joint on the card, the black line here, and then we have a tape measure attached to the track on the bottom. So for example, the first data point is at 740. So you're gonna align so you're going to align the black line on the card with the 740 line on the tape measure. So that's 740 position. So that's actually 740 millimeters, which is 74 centimeters. So for each of the 8 positions, you are going to record the absolute value of the voltmeter readings. So no negatives. For example, this one is minus 22, and this is minus 22 millivolts. So you're going to take the absolute value, which is 22 millivolts, as the first voltage reading for the first position. So for each of the 5 trials, record the voltage when the card is at each of the positions listed. And remember to take the average as the EMF readings for each trial. So in this experiment, we are assuming that the velocity v of the cart is constant. However, in each trial, the cart experiences a slight but measurable positive acceleration. So how do we minimize this impact of experimental error? So that's why we are using averaging a number of data points. So I'm sure you are familiar with the pivot tools on the top right corner. So first, we're going to use a vertical ruler to measure the height of the loop. So when you are measuring the velocity of the cart, you can use the horizontal ruler
and the timer. So you can align the horizontal ruler with the card, and you can zero the timer and start playing. And you can move frame by frame until like the metal rod here aligns with 100 millimeters, which is 10 centimeters. So that's the distance the card moves on the track is 0.1 meters. On time elapsed is 0.93 33 seconds. So using the distance it traveled 0.1 centimeters and the time, you can calculate its velocity. So next, you're going to construct the data table in order to create a graph that verifies our expression for Faraday's law, the V equals epsilon equals NBHV. So make sure you label your columns and horizontal both axes, and including the correct units, and to perform the linear regression. Notice that use absolute values for epsilon to make all values positive. Ignore the negatives. So also be sure to calculate and record the average voltage for each trial, and calculate the magnetic field strength B in the magnetic gap. The units are in Teslas. So don't forget that there are 8 loops in the coil. So in the third section, you're going to measure the magnetic field using the Lorentz force. So you can compare the measurement of the magnetic field strength using the concept of the Lorentz force with the previous sections. So in this video, the same magnetic gap assembly from the previous video is placed on a scale to measure the force caused by the current flowing through a conductor immersed in the gap. So you're going to watch the video once without trying to measure anything. So you can notice a few important details like which readings on the power supply is the current, and which one is the voltage. Also notice that the scale on which the magnetic gap assembly rests is measuring mass in grams. So finally, notice that the scale reading is not 0 when there's no applied current. And when you are graphing, you make sure you are converting the scale reading in grams to a force in newtons. And you're going to convert the scale force F to the magnetic force. So you construct data tables and create a graph that illustrates our expression for the Lorentz force. So F equals ILB. And make sure you label both axes and include the correct units. And you're going to prepare this graph and perform the linear regression. And you're going to use the slope to calculate the magnetic field B. So you will need to measure the length of the wire using the ruler too. Okay. So this ruler will tell you the length of the magnetic gap. Finally, you're going to compare the values for the magnetic field strength from the two methods.